Okay, so today's lesson on Friday, February 14th, and the Monday we come back from break is on the unit circle. And this is designed to allow us to do trig on any angle, no matter how big or where it lies in the unit circle. What we're going to do is essentially take an entire circle and draw angles of rotation in it. And as we draw those angles of rotation, we're going to make the radius of the rays that land on the circle a certain size. Specifically, the size that we're going to choose is 1, and that's why this is known as a unit circle. So we're going to be drawing in onto our unit circle several angles of rotation. And the first one that I'm going to draw will be that angle right here, and I will name it theta. Now, when I draw theta into this coordinate plane that happens to have a unit circle on it, what I find is that there's a point on the angle that happens to hit the unit circle. And what I'm going to do is I'm going to take those 2 points, and since I know that the radius of a circle is 1, I'm going to use those 2 points to identify certain parts of the ray. The most important part that I'm going to be identifying is this one right here. We will frequently refer to this as a point P on the unit circle. Technically, they could use any capital letter that they wanted, but point P will be the one you will see most commonly. The next thing that I'm going to do is I'm going to draw in a set of paths. Now keep in mind that this is a circle, so the radius of the circle really exists. It has length, it has distance, and it's 1 everywhere. But the paths that I'm going to draw are going to be the paths that I would take if I wanted to get to that point P on the unit circle that also happens to lie on the coordinate plane. Now, if I were to label point P, it would have coordinates x, comma, y. You'll notice both x and y are shorter than 1 because I have not gone out as far as the point 1 on the unit circle, nor as high as the point 1 on the unit circle. But what I can do is put an x here because it's the distance I traveled to the right, and a y here because it's the distance that I traveled to the north. Once I've done that, I actually see that what I have is a right triangle whose right angle is right there, and here's the important part, whose paths don't really exist. They were directional distances designed to get to the point P. But it's still a useful right triangle and can be used as well as and along with the Pythagorean theorem to find any side of the triangle whose sides are x, y, 1, which is to say that x squared plus y squared will definitely give me a 1 squared, but I don't need to write that. Now, having said that, I can also do trig on the angle theta, which happens to touch the origin and will always in unit circle trig. And I can say that the sine of theta would be the opposite side, known as y, over the hypotenuse, which happens to be a 1. That means that the sine of theta is y. That means that y is the sine of theta, and that means that I could rename or replace the y with sine theta. Likewise, if I were to take the cosine of theta, I would find that it is the adjacent side over the hypotenuse, or x over 1, and that means that x is the cosine of theta, which means that I can replace or substitute cos theta in for the x coordinate. In short, what I've just said is if this point P lies on a circle whose radius is 1, then the coordinates of point P are guaranteed to be the cosine of this angle and the sine of this angle. Point P will be a sine and a cosine. The y value is the sine, the x value is the cosine. Now let's go back for just a minute to this point right here. That point right there was on the unit circle and its coordinates were 1, 0. The angle associated with that particular point would be an angle of 0 or 360 degrees. Take a moment and on your calculator, would you please type in the cosine of 0 degrees. Now would you type in, please, the sine of 0 degrees. What you'll find is that the cosine of 0 degrees is a 1, and the sine of 0 degrees is a 0. Simultaneously, do the same thing for the sine and cosine of 360 degrees. What you'll find is that the cosine of 360 degrees is a 1, and the sine of 360 degrees is a 0. Now let's examine some other points that happen to lie on the unit circle. Let's begin with our next quadrantal angle, known as 90 degrees, or the point 0, 1. Now this 90-degree angle that lies on the unit circle would have as its cosine 0, meaning if you were to type cos 0 into your calculator, you would find that the answer was 0. I think I misspoke. You want to type cos 90 into your calculator. And if you type sine 90 into your calculator, you'll find that the answer is 1. Let's move along through the unit circle and identify the points -1, 0. This would be the cosine of 180, and this would be the sine of 180. If I were to keep going through the unit circle and identify the point 0, -1, I would also find that this would be the cosine of 270 degrees, and this would be the sine of 270 degrees. The next thing we need to add on to our unit circle trig is a different angle of rotation. I'm going to do this on a fresh sheet of paper so that you can see how it plays out, and I'm going to draw a new circle so that I can put a fresh triangle into my unit circle. And this triangle is going to originate with the ray that looks like this. My initial side is over here on the positive x-axis. My terminal side is over here in quadrant 2. But once again, drawing in the paths that I would take to get to this point, known as P on the unit circle, I would find that the paths still, indeed, give me a right triangle. Once again, it's worth noting that the distance that represents the length of the radius is a true distance. It's really there, it's part of the circle, and it can never be a negative number. On the other hand, these two black dotted lines are directions. This is the direction that I traveled along the x-axis to the left, and this is the direction that I traveled along the y-axis to the north. Since they are directions, they don't really exist. They are paths used to get to the point P. And you'll notice in this case that x, since it's moving to the left, will be a negative number. That means that the cosine of anything that lands in the second quadrant of the adjacent side over the hypotenuse will be a negative over a positive or a negative number. But I can still type in or draw in an angle named theta, and the cosine is still x over 1. It's just that in this case, x is negative. So let me move my point here. Can I separate these? I can. And I am going to write in that the negative cosine of theta is over here, which is to say that when point P was over here, the cosine of theta, as long as theta was the same exact size, was the same value as this cosine, this one will just be negative. And on this particular cosine point right here, the sine of theta, which was, as long as these two thetas are exactly the same size, it will be exactly the same number as this angle right here. Some examples to help you see what kinds of angles that I'm talking about. If I made theta 30 degrees in this angle and 30 degrees in this angle, then the angle of rotation that I would be referring to in order for those two thetas to be the same size would be the supplement to 30 degrees or 150 degrees. What that means to you is that the cosine of 150 degrees and the cosine of 30 degrees will have the same value, but this one will be negative. Moving right along, if I were to draw an angle of rotation into the third quadrant, I'll do that on a fresh sheet of paper. I could see that what I would find is that here's my unit circle. Here's its radius of 1. Here are my rays of my angle of rotation that's coming all the way down to here. And here is the path that I would take to get to that point known as P on the unit circle. And what I would find in this particular case, again, keeping in mind that theta is still the same size as it was in all the other angles, x is moving to the left, therefore x will be negative. But in this case, y is also a negative number because it's moving to the south. So the point named P right here would be a negative value for cosine, and the point named P right here would be a negative value for sine. Now that doesn't mean that I need to type in that negative. It means that if you take the sine or cosine of anything that lies between 180 and 270 degrees, your answer will be a negative number. Finally, if I were to draw in a unit circle that had an angle of rotation that lies in the fourth quadrant with a ray that begins on the positive x-axis and comes all the way around into the fourth quadrant, the path that I would take to get to that point would be a positive movement followed by a negative movement. Point P, therefore, would always be a cosine whose value would be positive, here's theta, and a sine whose value would be negative. What we're going to call these is the angles in the bow tie, because if we go all the way back to our first picture, that means that we can really draw 4 unique triangles, 1 in each quadrant, and put in 4 theta valued angles that have the same value, so that my 4 right triangles are congruent. And if I were to color in those 4 right triangles, they take the shape of a bow tie. Now, calling them the angles in